Hello everyone, this is Ravi Kiran here from EDS Technologies who is welcoming you today to this webinar of Scalable Saber Simulation Solution for Electric Vehicle and Power Electronics Design. So this is the topic for our today's webinar, and why I would like to say that I would like to say the relevance of this particular thing today is very important here to notice. See, with the recent developments in the EV segment, and as we are adding more, we at EDS Technologies are adding more EV companies to our customer list. We believe that this is the right time to introduce our Saber suite of solutions from Synopsys. We strongly believe that Saber simulation solutions will assist all our EV customers and our power electronics design customers very well in improving their design and simulation methods. With this brief relevance of it, I would like to start the session by giving very brief about EDS Technologies, who we are and what we are doing in India. Can we go to the next slide, please? Yes, thank you. Yes, the EDS Technologies, we are a 25-year-old organization, and with our innovation, technology, quality, and timeliness in our deliverables to all our customers, today we are proud to say that we have acquired more than 1,500 customers across the country, from north to south, the east to west of the Indian Peninsula. And the strength of our customer success is today is about 150 plus associates whom we have and are spread across the country. And another main success, what the reason for our success today is that the kind of flexible business models what we offer to our customers and to our multi-location presence. Here, I would like to say, I'm happy to say that today for this webinar, I see that the customers are joining from about 15 cities across the country. And welcome all of you once again for this webinar from all the cities across the country who are joining today. And next slide, please. Yes, thank you. Another one of the main reason for our success till date at EDS Technologies is our total solution offerings on the business solutions. Today, our business solutions range from mechanical CAD, whether it's some CATIAs, to our EDA solutions to PLM solutions, and extending our solutions to the 3D printing and our e-learning solutions. Our wide range of solutions today are helping all our customers to improve their efficiency and from having a total solutions from EDS Technologies. And to achieve this, we have strategic alliances like Synopsys, who are the leaders in EDA, and other various leaders in these segments who are the best to second to none. And with these alliances, we are able to offer better solutions, greater choice, and faster turnaround. So with this brief about EDS, 2 slides introduction of EDS Technologies, I would like to take this opportunity to introduce our Synopsys team members who are part of this webinar today, who is going to present the total Saber solutions, how it's going to be helpful for the electric vehicle customers and the power electronics design customers. So we have here with us today Gobi, who is the manager application engineering at Synopsys, and who is responsible for the Saber suite of product line. Gobi has been working with Synopsys for more than 10 years and with a total experience of about 2 decades. In these 2 decades, he has acquired various skills in the area of electrical design systems and simulation verification methodologies. And he has done his master's from NIT Trichy. And along with him is joined by Mr. Balaji, who is a senior application engineer, who is also similar expertise and experience like Gobi, and who has done his masters from IIT, Indian Institute of Technology, Mumbai. And today he is the responsible for Saber suite of products at Synopsys. And mainly his area of interest includes the design and analysis of new power electronic converter topologies. So with this brief introduction of Gobi and Balaji, I hand it over to Gobi to start the technical session, Gobi, and with a brief introduction about Synopsys.
Thank you so much, Ravi, and thanks for everyone in the call for your time for this webinar. And once again, thanks, Ravi, for the initial introduction. Yeah, I will start with some high-level introduction about our company, Synopsys. Synopsys is a multinational company with a revenue of 3.4 billion as of FY19, and we just had the FY20 results recently, so this is a bit dated. You could see the revenues are increasing year after year, and we have been doing a great job in the area of EDA. We have about 14,000 plus employees worldwide, and we have 3,000 plus patents, and we operate at 130 different offices across the world. And in India, especially, we have about close to 3,000 employees now, and we operate mainly from Bangalore, Hyderabad, Delhi, Noida, and Mumbai. And this is the agenda that I'm planning to go through today. And we have broader team and a lot of people in the call. If you have any questions, you could reserve your questions towards the end of the session. And also, if possible, you could put in your questions through the chat or questions window, and the coordinator will monitor all the questions and we will try to answer. And so yeah, we'll first see why simulate and why Saber specifically, and what are the typical design flow, and what are the typical requirements in each stage in the design flow, and how Saber can meet those and give you a comprehensive solution. And then we will have a summary. And then of course, Balaji, my colleague, will be giving a detailed demo about this tool and how it helps for the EV design and power electronics design. And at the end, we will open up the session for Q&A. And if you're not able to get all the questions answered, if you would like to contact us, we are also giving the contact details in the last slide, so you can continue to reach us. Okay, let's see why simulation in first place and why one should consider Saber. So the biggest reason is that electrification is increasing all over, and the designs are getting more and more complex with electrical and electronics content nowadays. Especially in the automotive industry, you will see all the companies are moving towards electric vehicles or hybrid vehicles, and same thing is happening in the aerospace industry. You hear more electric aircraft projects all across, and the same thing applies to other sectors such as energy, consumer, industrial, and medical, and so on. And in all of these verticals, power electronics is the center of focus, and that is really growing with a lot of complexity and advancements. And with all this, we cannot rely on the hardware testing because it's not just efficient, and it's not going to complete all the scenarios for testing. And it's going to be very expensive, time consuming, and definitely you won't be able to cover all the testing scenarios. Some of the testing that you want to do might be even harmful to do. That's where the simulation is pitching in. And having said that, there is a lot of simulation tools in the industry, right? And especially there are a lot of tools which are space-based, but typically space-based tools are often slow, and especially when it comes to the power electronics, which is the key in the EV design, they are often not giving enough details for the frequency domain analysis, which is the key to check the stability of your design, the control circuit. And there are a lot of other various individual separate point tools, but there is not one single tool which can meet your complete simulation requirements when you go through different stages of the design. So you start with basic design, and then you evolve your design like you see in the B diagram here. So there is no single simulation tool that is available which can help you with all of your requirement throughout. That's where Sabers comes in, where it provides a comprehensive simulation environment across the design flow. And this tool is not just new in the market. This is well-proven tool, which is there in the industry for 25 plus years, and which is already proved for superior performance and accuracy. Yeah, so definitely simulation is a must, and Saber is the best. We will see why in the coming slides. So we have seen a little bit about the design cycle in the previous slide, and design cycle um, starts with making some initial modules first, and then make the system design by putting some basic modules together, and then people do some basic analysis, behavioral analysis, and stability analysis, and so forth. And then people evolve with further details. For every component, they can put in the physics-based models as per exactly as per the component that one is using as per the data sheet. And then also the design can further evolve from a simple subsystem or a system into a system of system and multi-domain. It can go much beyond power electronics or much beyond one particular domain. And then apart from the nominal analysis, people also have to do a lot of advanced analysis, such as reliability analysis for various corner cases, right? So when you are having such different stages in the product development, the simulation requirements are different at different stages. When you are looking at the initial early exploration of your design, what you need is generic models. You don't want to spend time on getting into every detail of the model. So you want to have some reasonable generic models with which you are able to validate your design and get your proof of concept done quickly with high performance. And you don't have to play with a lot of simulation settings. You should be able to get the high level models put in to make the whole design and get them simulating quickly. And also the simulation tool should provide you very easy to use interface. So this is the typical requirement that one wants when they're starting at the left side. And then when they further evolve, when the basic analysis is done, when they further evolve, they would like to go for very detailed models, characterized models. They would want to import spice models based on the vendor data sheet or from the data given by the vendor. And also the design can become really complex. So we need the software tool to be able to handle really higher complexity, and the tool should be able to converge and offer some tuning knobs to have the convergence happening for bigger designs. When the design becomes really complex, the tool should be able to give you enough playing buttons to make the designs converge and get the accurate results. And also when you want to do a lot of reliability analysis, such as fault injection and worst case analysis, the tool should be able to offer all the high-end robust design capabilities. So this is the typical requirement. And like I said, it's very difficult to find a tool that can support all of your requirements like this. So our new tool, Saber EXP, which is an entry-level tool, will be able to help you with your initial design exploration. And this tool is going to be really great for all the power supply designs, power converter designs, and motor drive designs. And this tool, Saber EXP, is based on the piecewise linear models, and also the solver is PWL solver, which will give you high performance. And especially for the stability analysis, we have an analysis called PAC, with which you will be able to do the AC simulation to get the border plots to understand the stability of the design. So this will be able to give you first pass success because of the nature of the models and the nature of the simulator engine that we have in the EXP. And this tool is going to be very straightforward to learn, and you don't have to go through detailed training to get familiarity with the tool. And then when you move to the right side, where you want full power of complex designs, then you can go for Saber RD, which is great for detailed modeling. handling large designs and doing all advanced analysis. And this tool offers the capability to use high fidelity models. For example, if you are using any switching device such as an IGBT from a particular vendor, you will be able to characterize the model based on the datasheet curves very quickly. And that way you will be able to use high fidelity models rather than high level averaged models. And this tool will be capable of handling really complex designs. So that way you will be able to, just give me a minute. You will be able to do all the feature rich, high and robust design analysis with Saber RD. And having said that, we have a graduation path between the tools. So whatever the design you have done in Saber EXP for your initial design exploration, those can be easily exported to Saber RD automatically. You don't have to recreate anything. You can just do an export with a button click, and you will be able to get the equivalent design in Saber RD automatically created. And um, also the simulation settings will come through, so that way you will be able to have a seamless flow from Saber EXP to Saber RD. So these tools complement each other, Saber EXP and Saber RD, and they give you a complete a comprehensive solution from concept to the real product. Yes. So then, if you look at the electric powertrain, typical electric powertrain, these are the major components that you have. You start with obviously the battery, which is the biggest power source there, and then you have a lot of power electronics to convert that DC power into AC, which feeds the electric motor, and then a lot of controllers to control the power and the whole flow. And apart from that, you see a lot of sensors, mechanical components, actuators, ECUs, and so on. And also you have a lot of vehicle networks for communicating between the electronic control units. All of these can be easily designed and validated in Saber. Because Saber really gives a comprehensive solution. You can do all the power electronics and also the multi-domain designs using Saber tools. As you can see here, the batteries model using the Saber tool. We have a dedicated tool called battery tool here, which you can use for creating all the advanced chemistry battery models that are typically used in EV sector. And then you can also use Saber for creating the controller models. And we also have a software called Silver within Synopsys, which will be more into software of the ECU. You can even use that, and we have a co-simulation arrangement or FMU export facility, so that you can use both the tools, Silver and Saber, together, wherein the software side of the piece will be in Saber side, and the rest of the plant models you see here will be on the Saber side. And when it comes to the inverter, Saber is really great suitable tool, which has all the characterization tools for modeling your switching devices, so that your inverter can be very accurate. And likewise in the motor area, we have a lot of models in the library which can be useful. And also we can take the motor models from FEA tools like JMAG. So that's the additional advantage here. We have a good ecosystem. And not the electrical side, we have a lot of mechanical components and other components here, so that you will be able to realize the complete system. So you see some gearbox here, and the vehicle dynamics, and also the thermal side. So this is really a multi-domain tool which will equip to create your complete system and validate it. So with this comprehensive solution, it will really help you to increase your return on investment. So if you look at the industry today, this is the common customer flow. People have a lot of different tools for different purposes. So you have some tool initially for making your initial module design with ideal or generic components, and then you go one step further where you put all those modules together to make your system, and then you do some basic analysis with it, and then your design further gets complex, and then you end up with a large scale design where some of the spice-based tools will fail, and you have to look for really a powerful simulation tool. And then those offer often only the basic simulation capabilities. They don't offer any reliability analysis capabilities. So people end up using multiple tools. So that way you have to switch between tools. And when you switch between tools, you have to redraw the design at every stage, and you end up with multiple disconnected tools and multiple model versions. And obviously the reuse is very, very limited. And then you if you consider Saber environment, this gives one single standard environment. By adopting Saber EXP and Saber RD, you can just cut short your overall product development by months, and thereby you can save a lot of money as well. So because Saber EXP is an entry-level tool with which you can do the initial analysis, and with its seamless integration with RD or export into RD, you will be able to stick to one standard environment by which you can save months of time and cost. So now let's see a little more on the on both the tools. So Saber EXP is our entry-level tool for EV and power electronics, and obviously in terms of commercial, this will be a lot cheaper than Saber RD. If you don't need full power of Saber RD at the beginning, you could consider starting with Saber EXP, and when you reach a point where you have to do some advanced analysis or where you need some detailed models, you can just switch over to Saber RD. So the Saber EXP, which is our new tool, has a new solver, which is PWL solver, and all the models are PWL based for faster performance. And the user interface is pretty similar to Saber RD, but with a lot of additional enhancements. Those who are familiar with Saber tool can recognize that this is pretty much similar to Saber RD environment. The GUI looks pretty much the same, but a lot of additional enhancements is done here. For example, you'll be able to quickly grab the parts to create your design, and you'll be able to make various measurements after analysis is done quickly. So with Saber EXP and Saber RD together, you'll be able to make your complete EV design and power electronic designs. Here is an example for onboard charging module, where you have different stages in this, or different sections or portions of the design. For example, there is one section for DC-DC converter. For that, there could be a lot of topologies, a lot of alternative studies, what if analysis. So all those things can be very well done with Saber EXP. For the DC-DC boost converter, you have various topologies. All this, what if analysis can be done with Saber EXP to find the right topology. And when you're doing that, you could answer various questions. For example, what should be your switching frequency? So when you have higher switching frequency, you will have to you can just go for a smaller output filter. But when you are having a lower switching frequency, you can save losses. So AC related losses are going to be very less. So each will have its own advantage and disadvantage. All those things can be analyzed. And also on the inductor side, output inductor side, big and small will have its own advantage and disadvantage. If you have smaller inductor, you will end up with larger ripple current. If you go for bigger inductor, again size is going to be an issue. Then it will give higher conduction losses. And similarly on the MOSFET, you can do a lot of trade-off and various analysis on that. Likewise, on the output capacitor, you can analyze voltage ripple, and you can analyze the load transient response. These are all very much possible with EXP, and EXP will give a superior performance for medium to small complex designs. And once further, when you close the loop, you can also use Saber EXP to design and check the stability of your regulator feedback loop. We have an analysis called periodic AC analysis, which is great for checking the stability of your design. And also you can look at various alternatives here, like voltage mode control versus current mode control. Right. So after doing all these things, once you reach a point where you want to use a device based on the data sheet or based on actual characteristics given in the data sheet, you could just, continue to save, switch over to Saber RD. You can just export the design and continue there. You will be able to get a lot of pre-characterized models in Saber RD. For example, PW, pulse width modulated controllers and various MOSFETs, IGBTs, and a lot more capability like spice import, so with which you will be able to use specific device details when you go to Saber RD rather than high-level models. For example, for any switching device, we have a characterization tool. By looking at the data sheet, you will be able to understand the characteristics. You can just scan the characteristic curves from the data sheet, and you will be able to create accurate models. You don't have to ask so many details from the vendor to create a model. In first place, we have a lot of models in our library, so those are all ready to use models. Mostly those will be enough. In case if you don't find the model that you need, you can easily create one by using this characterization tool. Similarly, we have a magnetic component tool using which you can create various magnetic components such as inductor, transformer. These are all very common for the power electronics. So you can easily create those accurate models using our characterization tools. And also for controller unit, we have various ways of establishing it. You can create control unit natively in Saber by using state AMS utility tool. We also have a silver tool if you want to have the software and modeled in the other software which can come into Saber as an FMU, you can do that. And the other capability of Saber RD is into robust design. Apart from the basic analysis such as nominal analysis, you can do various advanced analysis which makes your design really robust. You can inject faults. The Saber tool is ISO 26262 certified. You can do various fault analysis, or people do DFMA in a different way, so that can be replaced with this Saber RD's capability. And you can do a lot of statistical analysis to take the variations into account, and you can do various corner case analysis using worst case capability in the tool. So let's quickly take an example here for robust design. If you take an electric vehicle, one of the biggest challenge or one of the main thing that everyone is attempting is to increase the range, right? So let's say you want around 300 kilometers with one full charge of battery. You make the design and you make the basic analysis, and you get the actual somewhere close to 250. There is a huge gap, right? And your goal is to increase the range to 300. How are you going to achieve this? So often people think, okay, we can increase the size of the battery. That's the easiest thing to do, but that's going to cost more money, and it's going to be heavy, and it's going to have a lot of other implications. So that's not the option always. We should also look at, with given battery size and capacity, how we can utilize the power more efficiently, how we can reduce the losses so that we can get more output out of the battery to increase the range. Saber gives a lot of advanced capability for that. So you can do a sensitivity analysis to find the parameters that have higher influence uh, on the range. So with that, you will be able to optimize the design really to tune the parameters such that which gives the maximum range. So with optimization capability, you will be you will be able to tune the parameters to get the maximum best range. Let's say with that, you are able to achieve from 250 to 300. But the next challenge is that it's not going to be 300 for all the vehicles, right? Because there is a production tolerance. The manufacturing tolerance will impact this. All of the vehicles will not be giving the same, and also the environment conditions will be impacting, like temperature and so on. So that's not enough. So we go further and give you capabilities like statistical analysis, Pareto analysis to further find the parameters that are to be tightened. So with all those advanced capabilities, you will be able to get your design as close as possible to 300, right? So that these are the capabilities for Saber RD. All right, so let's look at summary. So electrification and design complexity are the biggest drivers for simulation today, and we really need a comprehensive simulation solution because of this. And we cannot rely on hardware testing, or we cannot use different tools for every stage in the design flow. They're not just going to be efficient. So the solution is Saber. Saber really provides one single simulation environment from concept to real product, and that way you can have all your trainings efficiently done, sharing the results between your colleagues, between your suppliers. All this is going to be very efficient, and also the support is going to be very efficient. You don't have to talk to multiple vendors, and Saber is well proven, and it accelerates time to market, reduces cost. So when you don't need full power of Saber, you can start with Saber EXP, and then all this left side piece can be very well done with this entry level tool. And then when you reach a point where you need additional power, or where you need all the multi-domain system coming into play, detailed models, you can just go to Saber RD just with a seamless flow. So that way you will be able to get the complete comprehensive solution. Yeah, so definitely simulation is must with all the given reasons, and Saber will be the best. And Balaji will give you a live demo.
So thanks for the introduction, Gobi. Hi everyone. What you see right now on the screen is the Saber EXP window, which can be used for the conceptual level designs and perform simulations such as time domain analysis and periodic AC analysis to understand the frequency response of any periodic system. So what you see on the screen right now is a design which is a DC-DC converter forward converter topology. This is designed basically from the popular power electronics book written by Ned Mohan, Underland, and Robbins. So the idea here is to show you the capability of Saber EXP, which can perform transient simulations quickly using the various component models that are available in the library and are modeled for their generic functionality. So at the conceptual stage, as Gobi explained, we look forward for models that are generic in nature and help us to understand the behavior of the conceptual design, be it a power electronic circuit or a motor drive design. So using these generic components, we can model systems such as power electronic interfaces, DC-DC converters or AC-DC converters, or we do have capabilities to understand the motor drive designs using motors such as switched reluctance motor or induction motor and so on and so forth. This tool provides easier simulation options, easier and quicker simulation options to simulate circuits like active filters or even compensators that can help you to close the loop of a switching power supply. So these some of these commonly used topologies are available as design examples in the tool and help you to start off as without having to create from a blank schematic. So the tool provides quick simulation options for running transient as well as periodic AC analysis, which is for frequency analysis of the system. So the main intention of this tool is to make sure that the user can run simulations quickly. So for example, this simulation of a switching power supply just takes 350 milliseconds. So and provides quicker results. So what you see is an open loop forward converter design with a constant duty cycle operation. So we see that the output reaches a steady state value of 4.78 volt. So once we understand the design in its transient time domain, we often want to understand its frequency domain so as to design a closed loop system. Say, for example, this is a this is a forward converter design in open loop. So to create a closed loop system, whether we want to design a voltage loop or a current loop, we want to understand the frequency response of this system. So for that, the periodic AC analysis helps you to get the Bode plot of the switching system without having to linearize it. So a common practice is to create a small signal linearized system so as to run the frequency domain simulation. So in Saber, the periodic AC analysis helps you to use the same schematic that you have used to understand the time domain performance to get the frequency response analysis. So here what you see is the pack analysis output of the output signal. So if we look at the transfer function is the ratio of the output signal over the input signal. So the waveform calculator available in this tool helps you to easily calculate the Bode plot of the complete system. So the input is a sinusoidal source with an amplitude of 0.01 magnitude. So I just divided the output signal by the input, which will give me the Bode plot of the open loop forward converter design. To check to show you the accuracy, I have the results that are provided by the in the book. So I'm just opening the results that are given in the book. So the phase plot and the magnitude plot and the phase plot. So this, when you overlap the two waveforms, we can see that the accuracy of simulation has a close match between the simulation and the textbook result. So this way, a user can easily create Bode plots for switching systems without having to model the linearized system for the same schematic that you have analyzed for the time domain response. So with this, what we can, the user can easily understand the performance of different concepts that can fit for a given requirement. The tool gives you easy methods to add frequently used components like filter components of the inductor, capacitor, the voltage sources, diodes, and ideal switches. Similarly, once you create plots, some of the commonly used measurements are available just at the click of a button. If not, we have Saber provides more than 70 measurements like the ones that you see on an oscilloscope, so as to measure different quantities like voltage different levels, or the time domain measurements, even frequency domain measurements like phase gain margin, phase margin, which will be helpful for creating your closed loop designs. Apart from the measurements, the waveform calculator gives you an easy way to do manipulations on your curves. So whether you want to look at the magnitude of instead of dB, if you want to see the curve in terms of voltage, you can convert that to voltage, and then do some math, like if you have a noise waveform and you want to see the Fourier coefficients, you can just do an FFT on those waveforms. Similarly, do some absolute value, or many math functions are available in the calculator tool. So this way we can do a comprehensive understanding of the schematic, which is built using the generic components. So once we understand that the concept meets your requirements, then it's time to perform more simulations on the design so as to understand its so as to meet the robust design goals. In that case, Saber EXP offers an easy switch from Saber EXP to Saber RD using the export to Saber RD option. So all you have to do is just provide a design name, and the schematic is exported to Saber RD. So now what I'm showing is Saber RD tool, which has a similar look and feel of Saber EXP with the same ribbon concept which we commonly see in the Microsoft Office tools. All you have to do is open the design in Saber RD. So whatever work we have done in Saber EXP is simply exported to Saber RD and is now ready to use evolve into a design that is close to your hardware prototype. So as Gobi mentioned, Saber RD offers several options and features that can help you to enhance the design uh, that can simulate as close to the hardware as possible. So for that, the key is the simulation models. So like Saber EXP, Saber RD offers several different generic models that can help you to create functionalities such as control loops and so on and so forth. Then we have the component models that are pre-characterized based on the vendor data sheets. For example, MOSFETs or IGBTs and other components like PWM controllers or Zener diodes. So all those things are pre-characterized and you just have to add those into your design and make proper connections. So what you see on the schematic is an ideal switch. So we can simply change that with a MOSFET with similar suitable ratings. If you don't see a component in the component library, we have several characterization tools that can help you easily characterize components from their data sheets without having to go to the vendors and wait for them to provide you a model that can work close to the data sheet. So this way we can enhance the design that is made in Saber EXP to a design that is close to your hardware. So in the interest of time, I created a schematic that can replaces the MOSFETs with component model that is modeled in the power MOSFET tool. Similarly, a transformer that is modeled in the is modeled in the magnetic component tool. So the power MOSFET tool helps you to create models directly from the data sheet. This tool gives you various views that are necessary for creating a MOSFET model. For example, the IDVDS characteristics. All you have to do is just get the image from the data sheet and just trace the curves that are corresponding to each and every gate to source voltage. So this way we can create models directly from the data sheet, and each component comes with a data sheet. So those data sheet curves like IDVDS characteristics, IDVGS characteristics, then the capacitance curves are also available. The anti-parallel diode forward characteristic will be given. Then you can have we also see the gate charge characteristics. So all these things are modeled easily from the data sheet curves, and then the switching characteristics. So when we add all these characteristics into the component model, definitely the model is going to behave very close to the specifications that are given in the data sheet. So the model that is used in simulation is driven by the parameters that you see on the right hand side, and on the left hand side you see the accuracy with which the models are characterized. So this way, we can not only get models that are close to the data sheet, but also use the uh, simulation algorithm underneath Saber RD to simulate high fidelity models with higher complexity. The other model that I added here is the transformer model, which is modeled using the magnetic component tool. Again, we can see that the magnetic component, any magnetic component needs the core to be characterized and then the windings to be characterized. So by using this tool, we can accurately characterize the core properties and also the winding properties. In a similar way, we can model the rest of the, or we can improve the rest of the design so as to match the characteristics of a real component that is available on the hardware. The reason for this is to make sure that we can perform the tests that can be done on a hardware in a simulation platform. So apart from the models that can help you create a simulation circuit that mimics your hardware, we need different analysis. So for example, you want to understand the time domain behavior of your system. So when you turn on your hardware, you want to see what are the various waveforms on each and every component. So for that, Saber provides a transient simulation which will run the circuit in time domain. After that, we may want to look at the frequency response so as to design the control loop, or if you have the total overall closed loop system, you may want to understand the stability of your design. So that way, the periodic AC analysis will help you to understand the frequency response of the system. Then the other important things are to make sure that your design is according to the robust design is working according to your robust design principles, where you may want to understand the design performance with statistical variations. So Saber RD provides Monte Carlo simulations, which will help you to add tolerances to various components, and when Monte Carlo simulation is performed, your each and every component is component parameter is varied within the statistical variation that is provided, and the simulation is the required simulation is performed for each and every combination of your design. On a hardware prototype, the normal practice is to order maybe 10 to 15 prototypes, or even 100 prototypes, depending upon the cost, and then we perform testing on each and every device. So it is really time consuming. It requires huge cost to establish or to order the samples of the prototype, and at the same time create test setups for each and every prototype. So that way we save a lot of time by having a simulation model that can mimic your hardware and perform all the various simulations or analysis that you want to do on the simulation model, make your design robust, and then finally go to the hardware with all the design changes that are needed on your hardware, and then the number of hardware iterations will definitely be reduced by a huge amount. So Saber RD provides such complex analysis like Monte Carlo. Then we may want to understand the circuit's behavior with various values of, say, input voltage. So normally the input voltage will have a definite variation that is provided. Say for example, an 8-volt source can vary from 5 volt to 15 volt, or maybe the load can be a varying load which can vary in steps, or there can be a pulsating load which can vary from 0 to very high value, 0 to 100% within a given time. So there are various things that we may want to perform, which we may want to test on the hardware prototype. So for varying those parameters, we have a simulation analysis called parametric sweep. So when you run the simulation in time domain, we have an option to sweep the parameters of one of the device. If you want to sweep the parameters of multiple devices at the same time, Saber offers a simulation called multivariate analysis. So in that case, the design is tested by varying multiple parameters at the same time. So this is definitely an impossible task on a hardware prototype, because when you want to vary a parameter, definitely you have to remove the component, add another component with a different value. Similarly, if you want to test a MOSFET with a different MOSFET, for each and every test, if you have to shift these components from one part number to another part number, definitely it's a never-ending task, and involves huge manual effort. So to do such testing with multiple component value variation, Saber already offers a looping command called multivariate analysis, that help you to add multiple parameters and give you and you can specify different values for each and every parameter, and the simulator automatically runs between each and every iteration that you just provided and perform the simulation that you specified for the say for example transient time domain analysis in this case. Then sensitivity analysis was talked about by Gobi during his presentation, which helps you to identify the parameters that are that your objective function is sensitive to. So, for example, if you want an output voltage of 5 volt, but we are getting only 4.7 volt in time domain simulation with this design parameters, then we may want to see which parameter to vary so as to meet this 5 volt goal. So for that, we can define this objective function as 5 volt, or the output voltage as 5 volt, and vary the various components in your design and see which component affects the output the most. So that way, I mean, in this case, since it's an open loop system, we can simply change the duty cycle and reach 5 volt. But when you look at a closed loop system, definitely these internal components also will help you to decide the value. So for that, the sensitivity analysis helps you to understand the sensitiveness of your objective function for different parameters. So once you do the sensitivity analysis, Saber offers an option called analysis called worst case analysis, which will help you to optimize those parameters that the design is highly sensitive to, so as to get an optimum design. So by doing this, we are optimizing the design in the simulation platform itself, and hence that's why we say that by doing this kind of simulation on a simulation platform, this kind of analysis on a simulation platform, we can reduce the number of hardware iterations and hence save a lot of cost, resource, and time. So while doing all this simulation, all these various simulations, Saber RD offers a tool called experiments, which will help you to automatically run various tests that you want to perform on a hardware prototype. So as I mentioned, when Saber is capable of running different simulations so as to meet your goals of different types of hardware testing, we may also want to automate this process so as to just click a button and then wait for the results. So that way, the experiments tool will help you to create meaningful tasks, so as to run different simulations, different tests that you want to perform on your design, and then give you meaningful outputs. So for that, right now what you're seeing is an experiment that runs different simulations. So the time domain simulation, which is run with nominal component values. Then I'm running a vary analysis, which will run a transient analysis for each value of your output filter inductor. So depending upon the filter inductance value, the ripple current varies and its size also varies. So to test that, we just vary the inductance value and understand the time domain response. So Saber also has the capability to run functional safety analysis, which I'll talk about in after this in next few seconds. It also helps to run the Monte Carlo. So the other analysis that is added here is the multivariate analysis, which will vary different parameters that are listed here for each and every run. While doing these multiple simulations at the same time, we can use the multiple cores that are available on our laptop. Nowadays, what we see is each and every laptop comes with a minimum of 8 to 10 cores, and some workstations come with even 40 cores. So Saber RD has the capability to distribute these analysis into the number of cores that you have on your laptop. That way, if say for example, in my case, I have 8 cores on my laptop, so the time required to run 8 such iterations is same as the time required to run one transient simulation. So that way we can increase the speed at which the simulation runs, and hence get faster outputs. So it's not just about running the simulations. We can create meaningful graphs. Say, for example, in this case, I'm just running the vary analysis to see my output voltage. So I created a graph that plots the output voltage under all these different conditions. So just for in the interest of time, I have the results available here. So, okay. So after completing the simulation, we can see that the graphs are plotted, are available in the results tab, and so this is the voltage with just one single transient run. So the voltage is around 4.3 volt. Now, when we have this inductor varying between different values, what we have seen is that the ripple current changes, and because of the ripple current, the output ripple also has a direct impact on it. When we are running when we are varying multiple component values, we have seen that the voltage variation is much different. So in this case, the voltage varies from a value of around 4.3 volt to up to around 5 volt. So by this method, what we can see is the same design can be run or the design can be tested for different combinations of either the parameter values or the input values, or the say for example different loads, all at the same time, by simply creating experiments and configuring meaningful graphs. The other feature that I wanted to talk about is the functional safety analysis. So right now, functional safety is of prime importance in most of our automotive systems, and we do have a standard called ISO 26262, and Saber complies with that standard. So by performing fault analysis in simulation itself, we have two main advantages. One is that on a hardware testing, we cannot perform faults or add faults on each and every component on your hardware. Similarly, at times, some of the short faults can be catastrophic, and so when we run those kind of simulations on a simulation platform, definitely nothing is going to burn, but it will give you meaningful results so as to understand the performance of the design under such particular faults. So Saber allows you to easily create faults or configure faults using the faults tool. So when you look at the faults tool, the tool has capability to test the design under all possible faults on each and every component of your design. So in this particular case, we can see that just for this open loop design, we can perform up to 63 faults. So how you can generate these faults easily is using the fault generation tool. So this fault generation tool inside the faults tool helps you to identify the various pin faults, like the open faults, the short faults, then even parameter faults. So we can, if you want to know the effect of the drift of the value of a particular parameter, you can simply add parametric faults to your fault analysis and understand the circuit's behavior under different parametric conditions. So we have the tool automatically picks up all the different components that are added in your design, and once you click OK, it will generate all the faults for each and every component. Short faults, open faults, and so on and so forth. The fault analysis is not just restricted to the pin open or pin short faults. We can add digital faults on digital components, like if your digital value is stuck at 1 or stuck at 0, then we do have these options to add concurrent faults. So this is definitely not easy on a hardware prototype, because when you are trying to add say a short on one component and say a stuck at fault on a digital pin. So in those cases, definitely simulation will be the only option so as to run those particular test scenarios. So all you have to do is, once you add the faults, you just select them and add them to the concurrent fault groups. So all these faults are applied at the same time, and you can understand the circuit's behavior by running a transient analysis on the system. So this way, simulation provides you a lot of flexibility in performing functional safety analysis. So while adding these faults, the user has the flexibility to add or change the fault value. So the value of a particular component under fault condition can be configured using the fault value. Then you can specify a fault begin value. So when you want to run a fault analysis, a common practice is to add faults in steady state. So that way you can specify a fault begin time, which is the steady state of your system. So that by adding faults in steady state, we are making sure that that we are doing the same situation, or that we are testing the same situation that we do on a hardware prototype. Similarly, we can add a fault end value, which signifies an intermittent fault. Say a wire, two live wires touching together momentarily because of heavy winds, or a storm, or a tree falling on them momentarily. So those kind of things, momentary fault tests can also be performed by configuring the fault end value. So these are various options that are provided in the faults tool. So for this demo purpose, I just had a few faults which are say a digital fault on the comparator output. So this comparator output digital signal is converted to analog voltage and applied to the MOSFETs of the forward converter. So by applying a high signal at this pin, we are turning on these two devices continuously. So I mean, since this is a simpler example for demonstration purpose, we can clearly understand that when these two switches are continuously turned on, the transformer sees a DC voltage continuously applied across it, and hence it would eventually go into saturation. Similarly, there is applied a short fault on the diode, which is on the secondary side. So when I short this diode, what I see is every time the switch is turned on, this diode turns on, and hence the transformer sees a short. Then we have a combinational fault which combines these two faults. So both this fault is applied, and at the same time the switches are completely turned on. Let's see the results of that simulation. So okay, so I have this an experiment which runs fault loop by using this fault set, and I run a transient analysis. So so we would like to understand whether my system works properly or not under various faults that are inserted. For that, we can add some tests in your experiment, so as to see whether a measurement is within the limit or not. In this case, I have a current. The primary current is being measured and checked for a value 50 volts, 50 ampere. So my transformer is rated up to 50 ampere. So I want to see whether in each of these fault conditions, the current is limited to 50 ampere or not. So if I see, so a pass-fail criteria can be established by using this test task in the experiment experiment. Similarly, we can add graphs so as to see the eventual primary current. So I'm measuring the primary current and checking whether it is within 50 ampere or not, and also I'm plotting the primary current. So once I run the simulation, an experiment report is created showing me the pass-fail criteria under different fault conditions. So here with this is short diode, I can see that the condition is failing. So to understand what's happening, one other option that we can add is to record the measured value. I can even record this measured value by changing the log to S. So if I look at the current waveform, I can clearly see that I apply a fault at 5 milliseconds. So as I mentioned, the fault can be applied in steady state, and this is what you see. The fault begin value is configured at 5 milliseconds. So after 5 milliseconds, where my system is in steady state and I see a constant or steady state current flowing in my primary of the transformer, I see that on applying the fault, I see that the current is increasing to a very high value, which eventually leads the transformer to saturation and burn it because of overheating. Since we are running it in simulation, even though we see a few hundreds of ampere, we are safe, and we can clearly understand the problem problem in the design, that we need to add a current limiting device either in the input side, or while you design your closed loop system, you can make sure that the current is being sensed and the PWM controller is restricted. The duty cycle is restricted so that the current does not exceed beyond the rated value. So this way, we can perform functional safety analysis on your entire design that is close to your hardware, that is modeled with components that are close to your hardware components. So that finishes my demo, and yeah, I think this session is open to questions. A question from Srivalli. Bye.